Hi everyone, we're Group 7 and this is our final L3 presentation. The task was to design, manufacture and test an on-ramp driven glider with the objective of maximizing the glide distance. Throughout the design process, we strive to keep the design modular, easily adjustable, lightweight and the components easy to replace. The design is therefore based on a base plate on which all other components are attached. During the design phase, the dynamics of the glider on the ramp and in the air were modeled on MATLAB and several parameters were iterated upon in order to maximize the range. This was done along with a CAD design from which a weight estimate could be obtained. It was found that, with a ramp angle of 15 degrees, a 5:1 motor gear ratio, a NACA 6706 wing with an aspect ratio of 5, and a weight estimate of 35 grams, we would achieve an exit velocity of 3.5 meters per second and a total distance of 3.5 meters. The manufacturing process exposed certain weak spots in different components. Indeed, the way the bearing housings were attached to the base plate proved to be insufficient in accuracy to perfectly align the drive shaft. A new design included screws to remove the dependence on an adhesive. On the other hand, having an adjustable setting angle for the horizontal tail proved to be very beneficial. A lengthy testing phase enabled us to modify parameters in order to maximize glide distance. First, we tried to make the model steer straight and accelerate as fast as possible without slipping. Then the tail angle as well as the wing's mounting position were adjusted to stabilize the glider and maximize lift. 3 wings were tested. First, our initial wing design idea, with an aspect ratio of 5, made using carbon fiber rods and foam spars covered with solar film. Secondly, a foam plate with similar aspect ratio. And finally, a large foam wing similar to that of a hang glider, as the need of an even larger wing in order to maximize lift was ultimately recognized. Eventually, the wing chosen for final testing was the initial ribbon spar design, as it provided the most consistent gliding performance. The foam plate could not be effectively used due to longitudinal balance issues, as the tail angle required to stabilize the glider in flight caused excessive drag. Finally, the hang glider wing also proved difficult to stabilize both laterally and longitudinally. By balancing the glider for optimum ramp acceleration, flight performance was compromised and vice versa. The ramp angle was also chosen to be 5 degrees instead of 15 to maximize exit velocity. The final weight was 48.6 grams, which is 40% larger than predicted due to the addition of a second pair of wheels, electrical wiring and soldering material. So did the model fly straight? Did the model achieve the desired flight trajectory? Did the model stall? All these factors contribute to off-ideal performance. Comparing the most ideal flight condition case with the selected wing, the glider flew 2.6 meters compared to 3.5, as measured from the beginning of the ramp. This is due to the ramp exit velocity varying drastically from the predicted 3 meters per second to the actual 2. When the MATLAB model's exit velocity was changed to 2 meters per second, the predicted distance became 2.66 meters, a 2.3% deviation from the theory, which we feel is acceptable and validates the in-flight trajectory MATLAB model. The predicted exit velocity of 3.5 meters per second was, as mentioned earlier, not achievable in practice. This was due to friction losses unaccounted for during the design process. Additionally, the reaction forces at the front-driven wheel were smaller than expected because of a larger tail weight. Consistent performance on the ramp and in flight were hard to achieve. Difficulties were caused by uneven slippage on the ramp due to the shaft twisting, causing an uneven torque distribution and insufficient friction between the tires and ramp. To solve these issues, a stiffer steel shaft was used, on which 4 wheels with larger rubber O-rings were glued on. During the gliding phase, the glider was very susceptible to roll perturbations, which would cause it to deviate sideways. We tried adding dihedral, but it was relatively ineffective. To solve this issue, the roll angle as well as the setting angle of the adjustable horizontal tail was set such that the rolling and yawing moments produced balanced the laterally unstable glider. So what have we learned from this project? Our key takeaway is that not everything can be perfectly modeled. Many assumptions made for the simplification of the mathematical model will not hold true, such as the model flying perfectly straight or the model not stalling. A large degree of experimental trial and error is needed. Furthermore, it may be the case that the optimization of one factor may lead to the de-optimization of another. As mentioned earlier, the hang glider wing, when hand-launched, has very good glide performance. But when launched from the ramp, the wing's sheer size caused the glider to tilt backwards, resulting in the trailing edge scraping the ramp and generating friction. To fix this, we shifted the wing mounting position backwards. This, though, caused the aerodynamic balance to go off, compromising the gliding phase. Unfortunately, adding weight to balance the glider was not an option, as we were already close to the weight limit. Thanks for watching.